Well, this is 12th lecture in the series of mechanics of metal forming. If we recall the last lecture related to state of stresses and related issues, invariants, the equilibrium equations and all those things we discussed. This lecture will, the topic that is going to be covered are state of strains, the concept of strain, the compatibility equations, the physical meaning of strain, and then the invariants and all and related issues, as well as some of the problems it is there. So, let us start what we mean to say a strain at a point. In fact, the relative position of any 2 point, if we see in a body, a continuous body, and if it is changed, the relative position of any 2 point within the body, then we will say that the body is deformed or strained. When this distance between every pair of the point in the body, 3-dimensional body, there may be millions of points. So, if we take any 2 pair, if these pair of the body remain constant during motion or deformation, the body is said to be rigid. So, the displacement of a rigid body will consist what? It will consist, it may consist a kind of translation, it may be a rotation, it may be a translation as well as rotation, etc. Therefore, the rigid body, we call all these, we may call it as a rigid body displacement. So, the analysis of strain will consist what? It will consist the study of the deformation of the bodies, which is essentially a digit geometrical problem. It is not any other problem. So, because the geometry is changed, so it is a geometrical problem and is not related anything with the material property. So, the specification of strain at a point has to be either just like the elastic or physically plastic, it will remain same. Now, let us consider this figure number 1, which is showing a deformed body, and the body is a 3-dimensional volume, and let us consider the two arbitrary neighbor points like point A and B here, and in an which is unstrained body, this where the point A and B is there in the body, let us it is unstrained. So, when we strain it, that when the body is deformed, these point A and B will be changed to A prime and B prime, and therefore, we can put a vector. If we put a vector A prime which is deformed into the vector A prime dash. So, the component of A prime, vector A prime can be Ax, Ay and Az, and the component of therefore A prime dash can be your is equal to Ax plus delta Ax. Similarly, A prime y could be Ay plus delta Ay, and likewise A prime z could be Az plus A delta z, delta A z. So, these components is the displacement of point A as shown in the figure number 1. So, if suppose one want to calculate the displacement of this point A. So, if we take the initial displacement as u0, v0 and w0 across x, y, z directions. So, the initial displacement would be x0 prime minus x0, v0 would be y0 prime minus y0, and similarly w0 would be equal to z0 prime minus z0, and therefore correspondingly the point B can be u, that is u would be x prime minus x, v would be y prime minus y, and w would be z prime minus z. So, this is how one can have the displacement. Now, assuming the displacement to be a simple valued continuous function out of the coordinate axis x, y, z, the displacement at B, if we use the Taylor equations, and so the displacement of B can be written in the form of Taylor's equation by this set of equations by 2, number 2. So, that means if I take the W component, so by the Taylor's equation series, one can write the W is equal to W0 plus deva W by deva x Ax plus deva W by deva y Ay plus deva W by deva z Az. So, this particular equation, if we neglect the higher terms, because B is taken to be very close to A, very small displacement. So, higher terms can be neglected, and that is how the equation 2 looks like. So, the change in the component of vectors, that is A prime and A dash prime, can now be written as equation number 3, set of these 3 equations related to delta Ax, delta Ay and delta Az. So, for an example, this delta Az can be deva W by deva x Ax plus deva W by deva y Ay plus deva W by deva z Az. So, the same this equation number 3, the set of 3 equations can be written in the tensorial notation as delta Ai is equal to u ij aj. So, that represents the whole set of 3 equations, and therefore, the above transformation we call it as a affine transformation. And if it is further assumed that u, v and w and their derivatives are small, because the point A and B are very close. So, one can say that ux is equal to u, uy is equal to v and uz is equal to w. So, in that case it becomes an infinitesimal affine transformation, and that can be written into a matrix form, and therefore, uij, that is the component of the tensor, the displacement component, can now be written having 9 components like equation number 5, this matrix 5. So, for an example, the components are deva u by deva x, deva u by deva y, deva u by deva z, and similarly the second row deva v by deva x, deva v by deva y, deva v by deva z, and deva w by deva x, deva w by deva y and deva w by deva z. So, uij is a relative displacement tensor, and it is not symmetric. One can see these components are not symmetric in any way. So, this point is to be noted. If we see the rigid body motion which do not play any role in the analysis of strain as explained earlier. It is best to eliminate them therefore from the consideration. So, rigid body motions are characterized by the fact that the length of the vector joining any 2 points remain unchanged as said earlier, and consider the vector, say this particular vector a prime dash is, one can obtain it from a prime therefore by rigid body displacement. So, one can find out that a prime dash is square is a x plus delta a x square plus a y plus delta a y square plus a z plus delta a z square. And if we neglect the higher terms which is smaller, so multiplication would also be smaller, so one can neglect. So, this equation can be written as equation number 6, which is a prime a dash prime square would be your a square plus twice of a x delta a x plus a y delta a y plus a z delta a z. So, under rigid body motion, the length of the vector, two vectors, that is a prime and a dash prime, will be the same therefore. So, in that case equation number 7 can be written as a z delta a z plus delta a y delta a y and a x delta a x, which would be the sum of these three would be 0. Or one can also write down in the tensor form, that is a I delta a I is 0, and using the equation previous equation number 4, the same equation can gives, that is a I delta a I is equal to u I j a I a j, and that is equal to 0, and therefore one can expand the u I j a I a j as equation number 9. So, you can now see the del u by del x a x square plus these. So, 1 2 3 4 5 6, and this the 6 component would be equal to 0, and therefore this equation must be true for all values of a x, a y and a z. So, a necessary and sufficient condition that the transformation represents a rigid body motion would be what? It would be that del u by del x, del v by del y and del w by del z all are equal and it is equal to 0. That is the true that is the necessary condition, and in that case this forms the equation number 10, which is del u by del y is equal to minus del v by del x, and therefore del v by del z one can calculate as minus del w by del y, and del u by del z can be calculated as minus del w by del x. So, this equation and the conditions laid indicate that the rigid body motion tensor u I j is skewed symmetric, and that is u I j is minus u j I. That's, it's not symmetric, but it is skewed symmetric. So, if the second order tensor is taken, suppose the u I j is taken as the second order, and it can therefore be decomposed into symmetric and skewed symmetric part of the u I j. And then the skewed symmetric part will be represented as the rigid body motion, where whereas the symmetric part will be represented by pure deformation, and therefore u I j can be represented as equation number 11 here, this equation particularly equation number 11, and therefore u I j would be equal to your pure deformation as the symmetric part. So, that becomes half of in bracket uij plus uji plus half of uij minus uji, and that is equal to the strain ij plus that is plus wij. So, that is the component, the symmetric as well as non-symmetric, that is the skewed symmetric, where this epsilon ij is the strain tensor and wij is your rotation tensor, and it can therefore be written as the strain tensor can be written as equation number 12, which has again 9 components. One can see here from the equation number 12, and the rotation components, the rotation tensor can be shown as wij, which is shown in equation number 13 here. So, it is again one can see here the components. So, the diagonal component is 0, one can note here in the rotation the diagonal component is 0, and therefore, for pure deformation, if we consider the pure deformation where delta ai would be equal to strain ij and aj, that is equation number 14, and one can see here in this figure the same, because of if there is a shearing, let us see the equation number figure number 2, where the deformation for a pure shear case has been shown here. So, the two vectors, that is the vector a prime and a dash prime has been shown here, and corresponding the tensor notation therefore can be written as the strain tensor to indicate the affine tensor, the affine strain tensor in terms of the displacement. So, that one can now see from the figure 2 that the strain tensor, that is epsilon ij, can be represented as equal to half, and in bracket deva ui by deva xj plus deva uj by deva xi. So, I and j represents 1, 2, 3, and therefore, it represents a tensorial form. So, this is what is the basis of a strain tensor. Now, let us see what is the meaning of physically the meaning of these component in the strain tensor. So, let us consider in the figure number 2, where the vector which is parallel to x axis. So, that let us have the vector which is parallel to x axis, and therefore, ay would be equal to az, and therefore, that would be both would be 0, and therefore, ax is actually in fact a, and therefore, delta a I can be written as epsilon ij aj, and that gives equation number 16 as epsilon xx, that is in x direction. So, that would be delta aj divided by az, and that is delta a by a. So, here epsilon xx represents the change in length per unit length of the vector which is originally parallel to x axis. Similarly, one can get epsilon yy and epsilon zz will change in the length per unit accordingly in the direct which is parallel to y and z axis respectively. So, to consider the interpretation of the strain component as let us take epsilon ij, which is equal to the shear component of the strain, that is epsilon xy. Consider the two vectors a prime and b prime initially, which is parallel to the y and z axis respectively. So, if you see in the figure number 2, if nx, ny and nz, let it represents the unit vector across x, y and z coordinate axis, and therefore A prime can be written as ny ay and B prime can be written as nz bz because it is parallel to z axis. And after deformation, these vectors can be shown in the into A prime dash and B prime dash with the component corresponding to equation number 17. And therefore, one can see the equation number 17 here. For an example, the A prime is changed into B dash B prime B dash prime as nz delta bz plus ny delta by plus nz in bracket bz plus delta bz. So, if the angle between A prime A dash prime and B dash prime is theta, then from the definition of the dot product, like A dash prime B dash prime cos theta can be your A dash prime dot B dash prime, and which is equal to delta Az delta Bz plus in bracket Ay plus delta Ay multiplied by delta Bz plus in bracket Bz plus delta Bz multiplied by delta Az, and which is approximately equal to Ay delta By plus Bz delta Az, which is termed as equation number 18. Now, if we neglect the product of the vector increments, therefore, one can take this cos theta, one can take this cos theta as A dash prime B dash prime divided by A prime A dash B dash, and that can be further expanded in this form by the geometry here given in equation number in the figure. One can see the figure 3 after shearing, that is this how the point these vectors has been shown here and the parallelogram has been formed here. So, one can see cos theta can be represented as equation number 19 as delta By by Bz plus delta Az by Ay, and because we are neglecting all the increment except delta Az and delta By. So, again using equation number 14 earlier, we can write down delta Az is equal to epsilon xy ay, and delta By can be equal to epsilon yz bz. So, taking, say if I take alpha to be very decrease in the rigid angle from between the two vectors A prime and B prime. So, from this particular equation figure number 3, one can get cos theta as cosine of pi by 2 minus alpha, and that is equal to sine alpha, and because if the angle is very small, so that is simply alpha. This forms the equation number 21, and therefore, alpha can now be written as epsilon xy plus epsilon yz, and that is nothing but equal to twice of the epsilon yz. So, from this particular equation 19 and 20, one can see that epsilon yz represents half the decrease in the right angle between the two vectors that were initially directed along the positive direction of y and z axis. If the parallelogram is seen here, if the parallelogram in this figure number 4, where O prime, O P prime, Q prime, R prime is now rotated through the angle, an angle which is equal to epsilon yz about O. So, one can obtain the angle of shear. So, the angle of shear, if it is represented by phi, So, that would be the sum of the epsilon yz plus epsilon xy, and that is equal to twice of the epsilon yz, and this is what represents the shear element of which is parallel to xy plane, with epsilon yz represents the shear strain, and shear strain epsilon xy, therefore other strains could be epsilon xy, epsilon zx can also be obtained in a similar manner, just like in figure number 4. So, this is what the shear component of the strain is there. So, it is similar to direct strain component and shear component, and just like we have drawn the Morse circle diagram for the direct stresses and shear stresses, one can also do the similar kind of representation on the Morse circle for direct strain and direct shear part of the strain. Let us see the compatibility of strain. From the previous discussion, it is clear that if the displacement are specified as continuous function of the axis x, y, z, then the strain components can be computed very uniquely, and evaluation of the displacement u, v, w for a given strain increments is however very difficult, because several problems are encountered. Firstly, the solution obtained will not be very unique, because the strain represents a pure deformation, whereas displacements include rigid body motion which have no effect on the strain, as said earlier. So, the further strain vector, which is epsilon ij, can be represented as 6 equations in the terms of the basic displacement, like the previous equation number 12 and 15. So, these 6 equations have to be solved for 3 unknown quantities, usually u, v and w. So, these equations therefore will not have solution for any arbitrarily chosen strain, and some restrictions will have to be imposed on the strain in order to get a unique solution for the set of values. Now, let us consider a body, a 3-dimensional body having volume V, which is divided into infinitesimal cubes, number of such cubes. So, we have each cube can be separated from each of them and subjected to some arbitrary strain. So, if these strained cubes are put together, they will have no longer will be fitting, because now their positions has been changed, and it has a between some of the cube bound arises, there will be a gap, therefore which other way it may overlap. So, this purely suggests that there must be some relationship between the strain at different points of a body, in order that the body remains continuous after straining. In other words, one can say that the displacement must be continuous function of the coordinates, and these relationships in fact are called as the compatibility equations relations, or simply one can say as the compatibility equations, and it can be written as a set of equations as shown here in equation number 23. So, these 6 equations as shown in 23 are the basis of the compatibility equations related to strains. So, one can see for an example equation of the first part of the equation, which is del square del epsilon xx and del y square plus del square epsilon yy del xy square, which is equal to twice of the del square epsilon xy, and divided by dy x dy y. Likewise, these set of equations are called as compatibility equations. So, these equations, one can note that these are all independent of the material properties. There are nowhere any property related to material comes into equation, and therefore it is applicable to both, whether it is elastically deformed or plastically deformed, both material can be equally applied. So, these equations impose necessary and sufficient condition for strain components to give single valued displacement for a simply connected regions, for any region. So, for a multiple connected regions, the above equations produce necessary condition, but are generally it is not sufficient. So, this forms the compatibility equations strain. The second part, as discussed previously in the stress invariant, similarly there are strain invariants can also be here. Now, again let us consider the 6 component of strain at a point x, y, z as shown in figure number 5 here. So, this figure in fact is very similar to the figure number 6 and 7. If you recall back of the stress chapter when we discussed, where we represented the total stress as capital S, and therefore we are replacing the similar notations. So, here we replace capital S as your epsilon star, and for the stress, that is the sigma, is represented by simply epsilon. Now, the proceeding will be the same as we did the treatment in stress case. It can now be reproduced in the same manner and can now be written as the set of equation 24 here. That means epsilon x star can now be written as, which is equal to nx epsilon xx plus ny epsilon yz plus nz epsilon x zx. So, likewise these 3 sheets can be written, and extending the analysis further as done previously for the stress system, the cubic equation can be now written as equation number 25 as epsilon star cube minus J1. So, we represented I1, I2 and I3 as the invariants, stress invariant. Now, if we write J1, J2 and J3 as the strain invariant, so the cubic equation in the same fashion of the stress, one can write down as epsilon star cube minus J1 epsilon star square minus J2 epsilon star minus J3, and it is equal to 0. So, one can see here in figure number 5 that this is the point where the strains and their component have been shown, and it is a plane AB is a plane which cuts the axis. So, the strain has been shown on this particular infinitesimally small tetrahedron, and this forms the basis of a cube here in the in figure number 5b. So, we find the strain invariant as J1 and J2 and J3, and J1 is equal to epsilon xx plus epsilon yy plus epsilon zz. Similarly, the J2 is epsilon xy square plus epsilon yz square plus epsilon zx square minus in bracket epsilon xx epsilon yy plus epsilon yy epsilon zz plus epsilon zz epsilon xx. And similarly the third strain invariant is epsilon xx epsilon yy epsilon zz plus twice of epsilon xy epsilon yz epsilon zx minus in bracket epsilon x epsilon yz square plus epsilon yy epsilon zx square plus epsilon zz epsilon xy square. So, one can then derive in a very simple manner called as the principal strain form. So, in the form of the principal strain, the same equation number 26 can be put as equation number 27 as J1 to be epsilon 11 plus epsilon 22 plus epsilon 33 which is equal to 0, and J2 would be therefore minus of in bracket epsilon. So, because in case of principal strain the shear component would be 0, and therefore from the equation 27 if we component the shear component means x, y, y, z, this is all becomes 0. So, one can get this value, and therefore the J3 is written as epsilon 11 epsilon 22 epsilon 33 simply. So, this is what the basis of strain invariant. Now, similar manner we decide the total stress was consists of two component, deviatoric part of the stress and hydrostatic part of the strain. Here also we can now define as the strain deviatoric tensor. So, it can be now similar to the stress tensor can be written as equation number 28. Therefore, deviatoric tensor can be written as epsilon ij which is equal to epsilon ij prime plus half of the epsilon ij and chronicle delta ij. So, here epsilon ij prime represents the change in the shape of the deviatoric component, and therefore, one can say that the epsilon m which is the mean, which is similar to the hydrostatic part, is equal to 1/3 of the epsilon ij and deviatoric part, and which is the spherical or hydrostatic part of, and therefore epsilon m can be written as equal to sum of epsilon 11 plus epsilon 22 plus epsilon 33 divided by 3, and therefore one can derive from equation 28 here the epsilon xx prime, epsilon yy prime, epsilon xz prime and epsilon xy prime. One can derive it just simply by minus and substituting the value of epsilon m, one can get this set of equation 29. So, this stress deviatoric tensor can be also written corresponding to the stress part. This deviatoric tensor stress it can also be written for the strain invariants part. So, that means one can similarly write it for J1 prime, J2 prime and J3 prime. So, this is written here in as equation number 30. So, J1 prime is 0, J2 prime is 1/3 in bracket J1 square plus thrice J2, and similarly the J3 prime can be 1/27 twice. So, one can see this equation number 30 corresponding to the shear, there it is almost same. So, one can then also write down this equation number 30 for the direct strain component in the invariant form. So, J1 prime would be 0 here and J2 prime would be given this long equation 31 set of this equation, and similarly the J3 prime can be shown here. It is a long equation here again, and but I would read for you that this equation where the J2 prime, if you compare, it is written as this epsilon xx square plus epsilon yz square plus epsilon zx square minus in bracket correspondingly epsilon xx prime, epsilon yy prime plus epsilon yy prime, epsilon zz prime plus epsilon zz prime, epsilon xx prime, and which is nothing but 1 by 6 of that epsilon xx minus epsilon yy square plus epsilon yy minus epsilon zz square plus epsilon zz minus epsilon xx square plus 6 of in bracket epsilon xy square plus epsilon yz square plus epsilon zx square, and therefore it is a long, and similarly the J3 prime can also be written, and it comes out to be 1 by 27, and under bracket 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18, almost 18 terms are there corresponding to the J3 prime of the invariant strain tensor. So in terms of the principal strain, the same equation 31 can be reduced to J1 prime as 0, J2 prime as because the shear component would be all 0. If you remove the shear component like epsilon yz, epsilon zy, epsilon xy, epsilon yx, epsilon x yz, xz, and all these things would be 0. So J2 prime can be represented as minus of the 3 terms like epsilon 11, epsilon 22, epsilon plus epsilon 22, epsilon 33 plus epsilon 33, epsilon 11, and J3 prime simply all other would be deleted is 0. So it is simply the multiplication of epsilon 11, epsilon 22 and epsilon 33. So this forms the basis for the strain at a point, state of strain at a point, and you recall this treatment can similarly extended it for Morse representation. As I told you, the Morse representation is a graphical representation, so you can extend it the similar counterpart of the stress here as well, and you can do all the exercise which was explained in the previous lecture 11, where we took around 8 problems. You can also extend it for the cases where the strain tensor, elements of the strain tensor is given, and you can extend it for here also. So with this definition of strain, because now just like we have stress is equal to strain multiplied by Young's modulus, it is a very simple equation which is valid for cases within elastic, but when we enter into the plastic region, the whole deformation is consisting of the plastic and elastic component, and when the elastic component is very negligible, we are going to deal more and more with plastic part of the deformation in forming. So we must have relationship between this treatment, that there is whatever inform the invariants in form of the compatibility equations, and with respect to this definition of stress and strain, and therefore you require further relationship between the stress and strain in light of these two major topic as the state of stress and state of strain. So, subsequently therefore, we would be dealing with the treatments based on the relationship between stress and strain and for deformed bodies. So, this is what we would be covering in 13th lecture next time, and I once again would like to tell you that these objective problems which is given, you can evaluate on the web, where the you can understanding the part of the lecture, how much you understood, what you can evaluate. And I once again thank you for your patience hearing the lecture, but please give your feedback and suggestion so that we can further improve upon. I would also like to tell you that this project has been funded by national mission on education through information and communication technology, New Delhi Ministry of. So I would like to thank them also for their help. Thank you very much.